Okay, continuing with the calculator portion of this practice AP test. A does not equal to 0. Find the limit as x approaches a. So if we want to evaluate limits algebraically, first thing we do is we plug in that target x value and see what that provides for us. If it provides us an expression that represents a real number, then that's our answer. But if we get 0 over 0, then that means there's a hole, that there's an answer at the end of this problem. We can factor, reduce, reevaluate. So let's see what happens here. We'll plug a in for the x. So we get a squared minus a squared over a to the fourth minus a to the fourth, and that's 0 over 0. So this is not non-existent. That means there's a hole, which means that if we eliminate the hole, we should be able to arrive at a real number or a real expression value. So we're going to see what we can do. This is something that we can factor. So we go back to our original expression. We could do difference of squares there, but I'm just going to go ahead and do difference of squares for the denominator. I get x squared minus a squared times x squared plus a squared. And I don't have to go any further with the numerator because I see a perfect match. I'm going to reduce. I'm left with 1 over x squared plus a squared. Reevaluate. Replug in a in for x. We get a squared plus a squared. So combine like terms. 1a squared plus 1a squared is 2a squared. And that's our limit. Answer choice B. 84, we have a population that grows in accordance with our differential equation. dy dt is equal to ky. Population doubles every 10 years, so I'm going to gather information as order pairs. T being our independent variable, population being y, but I'm going to let initial population be some unknown value of p. And then the population 10 years later is going to be twice that value. So back to my differential equation, dy dt is equal to ky over 1. I'm going to cross multiply. I get dy equals ky dt. I want to separate my variables. So anything involving with y, I'm going to leave on the left side. Anything involving with t and any coefficient, I'm going to leave on the right side. So divide by y. I can set everything up, apply natural log on the left side, power rule kt plus c, raise both sides base e, drop the e in natural log, becomes absolute value of y. This becomes e to the kt times e to the c. E to the c is just a constant. We can push the constant out in front. And now we have a general equation to work with. I'll plug in my initial order pair, 0p. If I get p equals ce to the k times 0, which is c is equal to p. I updated my equation. So now I'm going to use the second order pair to help me solve for k. 2p plugs in for y. 10 plugs in for t. The p's cancel out. I'm left with 2 is equal to e to the 10k. I'm trying to solve for k, but k is sitting up as an exponent. So I'll take the natural log of both sides so we can take advantage of log properties to bring that exponent down in front. So once we have natural log of both sides, we can bring that 10k down in front. 10k times natural log of e, and natural log of e will just go away to be just 1. Divide both sides by 10. We get natural log of 2 over 10, which is 1/10 natural log of 2, and in the calculator we get 0.069. Okay, 85. We have a function that's continuous on the closed interval from 2 to 8. Values are given in the table. Using the subintervals, what's the trapezoidal approximation? So trapezoidal approximation, we have 3 subintervals, so we're going to have to find 3 separate areas of trapezoids. Each area of a trapezoid is width over 2 times h1 plus h2. So I'm going to first separate each or identify each of the subintervals there. And the difference between the x values will give me the width of each subinterval. So 5 minus 2, that's a width of 3. 7 minus 5, that's a width of 2. 8 minus 7, that's a width of 1. So piece by piece, I'm going to put into my formula here. Width over 2, so that's my first interval has a width of 3. So 3 over 2, height 1 plus height 2. So 10 plus 30. Second subinterval has the width of 2, 7 minus 5, width of 2, so 2 over 2. Height, the two heights associated with the second interval is 30 and 40, so 30 plus 40 goes there. And third subinterval has a width of 1 over 2, height 1 plus height 2. We clean all this up, and we get 160. Okay, number 86. Base of a solid in a region in the first quadrant is bounded by the x-axis. So here's the x-axis. The y-axis, that's a vertical line here. And the line x plus 2y is equal to 8. The cross-section is of a solid perpendicular to the x-axis. So there's a volume question. We're going to draw the length of the base, and the problem tells us how to draw that base perpendicular to the x-axis. X-axis is horizontal, so perpendicular must be vertical. So we're going to draw a vertical base that connects the two boundaries. So it's a vertical base. We know we're going to be doing top minus bottom. So the top graph is sitting on the diagonal line. And the diagonal line is not quite set up initially as y equals. So let's go ahead and do that. Solve for 2y, make 2y by itself, divide both sides by 2. We get negative 1/2 x plus 8 over 2, which is negative 1/2 x plus 4. So the top of this vertical base is sitting on the negative 1/2 x plus 4. So that's the top, minus 0, that's the bottom. And we have our base being negative 1/2 x plus 4. Okay. We're trying to build semicircles on top of this, this base here. So semicircle formula is pi over 8 base squared. We just put that base expression in for our formula. So we get pi over 8, negative 1/2 x plus 4 squared. But this only, let's see, this is not quite the answer here. This only gives us a two-dimensional answer, two-dimensional value. We want to find the volume, so we need a third dimension. So we're going to include integral on the left and dx on the right. That gives us that third dimension. So our antiderivative is from 0 to 8 because those are the bounds from the furthest left to the furthest right. And the rest we use our calculator. Volume is approximately 16.755 cubic units.